As physicists, we've enthusiastically guessed this second for more than a century. Beginning around 1916, this occasion marks a momentous accomplishment, offering a brief look into one of the universe's most charming and puzzling peculiarities: dark openings. These grandiose Goliaths, known for their monstrous influence, remain incredibly elusive. While they are epic in terms of their gravitational impact, they are almost undetectable to us, making them even more mysterious. One such dark opening, possibly weighing between 2 to 4 million times the mass of our Sun, may be the subject of this discovery. Over the past several decades, research on dark openings has transformed our understanding, taking us from a place of complete ignorance to one where we are beginning to get an intimate look at them. And now, things have taken an even more exciting turn, as physicist Michio Kaku has revealed that we have finally figured out how to look inside a dark opening. This discovery opens the door to an abundance of new data that could illuminate aspects of science we may have previously overlooked. Let us take a deep dive into the realm of dark openings and uncover what exists within them. While space is vast and infinite, the concept of dark openings raises countless questions. Before we delve into the specifics of Kaku's remarkable findings, it is essential to understand the fundamental nature of dark openings. Most people have a basic understanding of what dark openings are, but significant gaps in our knowledge remain. The theory of dark openings dates back to 1916, when Albert Einstein published his general theory of relativity. This theory predicted the existence of dark openings, but at that time the idea was purely theoretical. It was only about 50 years later, during the 1960s, that substantial evidence for their existence began to emerge. Scientists studying the star system known as Cygnus noticed an unusually bright blue star emitting X-rays. They discovered that this star was not stationary but orbiting a massive dark object. Upon further investigation, it became clear that these X-rays were being drawn into this object, leading to the coining of the term dark opening. This discovery was a monumental turning point because it confirmed that dark openings were not just a product of Einstein's imagination, they were real entities that existed in space. It became evident that we needed to study them more thoroughly. Researchers from around the world began focusing their studies on a particular dark opening in the Cygnus constellation, designated Cygnus X1, which lies approximately 6,000 light-years from Earth. This dark opening was several times brighter than the Sun and exhibited extreme density, with a gravitational pull so intense that even light could not escape. This is the defining characteristic of a dark opening, the ability to trap light within its gravitational grasp. The concept of a dark opening is both fascinating and terrifying. A dark opening is a region in space where gravity is so strong that nothing, not even light, can escape. Any object that ventures too close is pulled in, and once it crosses a critical boundary, it is lost forever. This inherent danger is why it is crucial to expand our understanding of dark openings. After the discovery of Cygnus X1, researchers launched an extensive search for other dark openings. Estimates now suggest that there may be over 100 million dark openings scattered throughout the Milky Way galaxy. However, due to their nature, these cosmic giants are extremely difficult to detect, meaning we do not have an exact count. What is clear, however, is that there could be millions of dark openings within our galaxy, highlighting their significance in cosmic research. The primary focus surrounding dark openings revolves around their gravity. Their gravitational force is so immense that anything that gets too close is gradually compressed to an extreme degree until it becomes a singularity. Simply put, dark openings function as cosmic vacuum cleaners, pulling everything in with an insatiable force. One of the most unsettling aspects of dark opening research is that if someone were to fall into one, they would be stretched into an elongated form due to the tidal forces acting upon them. This stretching would occur gradually, and the individual would perish before reaching the final stage of the process. So, to be clear, it is best to avoid falling into one at all costs. Even though the nearest dark opening is nearly 500 light-years away, questions still arise about the potential risks they pose to us. In 2021, a remarkable achievement was made when scientists successfully captured the first clear image of a dark opening. This particular dark opening was located in the M87 galaxy. The research team took numerous images over several nights, and by stitching these images together, they created a comprehensive photograph that revealed astonishing details. Interestingly, a dark opening is not just one giant void of nothingness, as many people assume. In fact, a dark opening consists of three distinct layers. 1. The event horizon. Once an object crosses this boundary, there is no turning back. It will inevitably be pulled into the dark opening. 2. The photon sphere, a region where light itself can be trapped in orbit around the dark opening. Any light entering this area becomes ensnared by the dark opening's gravitational force, unable to escape. 3. The singularity. The core where everything that falls into the dark opening is compressed into an infinitely small point. This is where the laws of physics, as we understand them, completely break down, making it impossible to predict what could happen. What is even more fascinating and unsettling is that no two dark openings are exactly the same. While they all follow this three-layer structure, the way they function can vary significantly from one to another. Typically, scientists rely on telescopes to observe celestial objects. However, when it comes to dark openings, this approach is impractical because dark openings are invisible. Instead, researchers study them indirectly by observing the radiation they emit, along with the surrounding gas and dust. Sending probes like Voyager to explore dark openings is also impossible, as anything that crosses the event horizon would be pulled into the singularity and crushed. As a result, scientists must study these extraordinary objects through a two-dimensional lens. All in spite of their intrinsically three-layered nature, one hypothesis in regards to the development of dark openings is that they are the consequence of imploding stars. When a star copies through its fuel, it can never again produce the energy expected to check gravity, prompting a breakdown internal, which can at last make a peculiarity. To additionally examine the idea of dark openings, NASA researchers turned their concentration to the center of the M87 galaxy. Here, cosmologists noticed a huge whirlpool of superheated hydrogen gas turning at a fantastic speed of 1.2 million miles per hour. The sheer power of this turning gas ought to have made it fly apart, yet it stayed in salvageable shape. Researchers guessed that a monster mass at the focal point of the system, gauging however much 2 to 3 billion times the mass of the Sun, was maintaining some kind of control. This mass must be made sense of by the presence of a dark opening. Anyway, dark openings may not simply be made by falling stars. In 1963, New Zealand mathematician Royer utilized Einstein's conditions to depict the elements of pivoting dark openings. Core's arrangement showed that, as opposed to imploding into a point, a turning dark opening would shape a slight plate, a peculiarity known as the ergosphere. The ergosphere is a locale encompassing the dark opening where the laws of physics begin to break down. Kay's answer likewise anticipated the presence of an Einstein-Rosen extension, regularly known as a wormhole. This theoretical passage would interface two separate districts of spacetime, and in certain speculations, it might really connect two parallel universes. If one somehow happened to fall into a dark opening, as opposed to being squashed, they could go through this wormhole and emerge in an alternate universe or even at an alternate moment. To comprehend how a wormhole functions, we should initially embrace the idea of spacetime. As per Einstein's hypothesis of relativity, existents are entwined, shaping a four-dimensional texture. Objects with mass twist this texture, creating a gravitational field that makes different items push toward them. Picture spacetime as a piece of paper. On the off chance that you put two focuses on it and define a boundary between them, that line addresses the way protests take through spacetime. If you had the option to overlap the paper, you'd make an easy route between the two focuses, similar to a wormhole connecting two far-off locales of spacetime. Wormholes are not only sci-fi, they are an immediate expectation of general relativity. Anyway, nobody has yet noticed one, and they are intrinsically shaky, likely falling very quickly. The potential for wormholes to act as movement pathways through reality has charmed physicists for quite a long time. While the idea of navigating immense distances in a moment or venturing through time is unquestionably thrilling, the difficulties are impressive. Einstein's unique hypothesis of relativity predicts that nothing can travel quicker than the speed of light, which puts an absolute limit on the practicality of wormhole travel. Essentially, with our ebb and flow comprehension of physical science, a specific kind of wormhole known as the CR wormhole, after Royer, has caught the creative mind of numerous. This theoretical wormhole would interface two far-off focuses in spacetime, potentially even connecting various universes or different moments in time. Critics, however, contend that the CR wormhole might be unsteady or difficult to navigate due to outrageous radiation and the powers at the quantum level. A few physicists bring up that Einstein's conditions, used to portray dark openings and wormholes, don't represent the quantum power that governs subatomic particles. To genuinely comprehend these peculiarities, another hypothesis that joins quantum mechanics with general relativity is required. Such a hypothesis, known as a theory of everything, could make sense of how the universe functions at every scale, from the littlest particles to the biggest vast designs. Michio Kaku, a main hypothetical physicist, has been chipping away at this unified hypothesis for a really long time. One promising competitor is superstring theory, which proposes that all fundamental particles are truly small vibrating strings. In this structure, the universe is viewed as an ensemble, with various particles corresponding to different vibrations of these strings. Superstring theory additionally provides potential clarifications for dark openings, wormholes, and other colorful peculiarities by exhibiting how strings twist the texture of spacetime. Regardless of its commitment, superstring theory remains exceptionally speculative, as it requires additional components of spacetime that we can't yet straightforwardly notice. These additional aspects could be minuscule to the point that they are effectively undetectable to us. A few scholars recommend that these aspects were more conspicuous toward the start of the universe, during the Big Bang, and that they fell as the universe extended and cooled. Superstring theory's potential to make sense of dark openings, wormholes, and the actual texture of the universe remains one of the most interesting wildernesses of present-day physics. As we continue to disentangle the mysteries of spacetime, dark openings, and the actual universe, there's no doubt that there is much more to learn, and perhaps much more to find, about the actual nature of reality. As we stand on the cliff of such historic disclosures, one key acknowledgement remains. We are just beginning to expose what's underneath. As far as understanding dark openings and their real essence, Michio Kaku's work in the field of string theory and the ideas surrounding quantum gravity have just begun to offer potential responses. Despite the fact that we've figured out how to acquire a more clear picture of dark openings through mechanical advances, such as the Event Horizon Telescope and new techniques for indirect perception, much remains outside our ability to comprehend. The frontiers of theoretical physics, specifically with regards to dark openings in spacetime, are still an incredibly dynamic area of investigation, where much theory and exploration await. Nevertheless, their undeniable role in impacting the texture of spacetime has become key to conversations about the beginning of the actual universe. As string theory proposes, the crashes of universes could lead to the creation of new ones, and dark openings could be essential in this cycle. Such a hypothesis could suggest that our universe might have been born from a collision of two previously existing universes, or maybe it might propose that we dwell inside a dark opening itself, an idea that would certainly flip our understanding of the universe on its head. If this idea turns out as expected, it could challenge all that we assume we know about the Big Bang, and we could begin to see dark openings as not just horrendous forces, but possibly creative ones that act as a gateway to different domains or parallel universes. While the possibility that dark openings could serve as gateways to other universes or even be the key to understanding time travel is tempting, this idea remains within the realm of theoretical hypothesis. The mechanics behind wormholes and the capacity to explore through them remain a significant mystery. Even if wormholes are stable enough to form, there's the question of whether the extreme radiation and forces near these structures would make them safe. Some physicists speculate that if we were to stabilize a wormhole, it could hypothetically permit travel through time or between far-off points in the universe, but that remains a distant dream, at least with our current technology. Furthermore, if we consider dark openings from the perspective of quantum mechanics, we're faced with even more intriguing questions. The behavior of particles at the quantum level is fundamentally different from what we experience at visible scales, and the laws of physics seem to break down completely when we consider objects like dark openings. This discrepancy between quantum mechanics and general relativity has been one of the most important challenges in theoretical physics. Theories such as superstring theory offer a possible framework for reconciling these differences by introducing extra dimensions and offering new insights into the nature of gravity. However, this theory has yet to be experimentally confirmed, and many of its predictions remain untested.